what we're going to do now is we're going to finalize this consolidation number one, first part of consolidation, part of the series here, by conducting some examples, right? We're going to do some examples where we're going to determine from the consolidation curve, that is, using the consolidation curve that we obtain in the lab for soil, we're going to determine the consolidation settlement of a layer in the field, okay? So we have to extrapolate from the lab to the field, meaning we're going to use the parameters that we have in the lab, we determine in the lab, to determine the consolidation settlement of the layer in the field. Okay, before we get to that, let's make an analogy so that you can see essentially what the consolidation curve is in terms of extrapolation. So let's say that we have a spring, and the spring is fixed down here, okay? And here we're going to place a weight. The spring has a stiffness K, okay? And the idea is that we want to know what the deformation of the spring will be if we place this weight here, okay? Or any weight. So you know this law, this is Hooke's law, that tells you that the force is equal to the stiffness times the deformation. Often this is written as F is equal to Kx. Okay, but here we have denoted the deformation as delta and the force as W, the weight. Okay? This means that delta, which is what we want to know what the deformation is given the stiffness and given the weight, is equal to the weight divided by stiffness. Okay, it's just algebra. So, if we wanted to plot this equation, this is the equation of a line, right? We could plot it like this. Okay? So, given any weight, we would get the relevant delta. This is a line. Y is equal to mx plus b, but b is the intercept, which is 0. So this line begins here, like this. What is the slope? Well, y is equal to mx, right? So m is the slope. In this case, the slope is k. Okay? And this is the same as for example, a concrete cylinder where you plot stress versus strain, and then you know the cylinder, the concrete cylinder has a curve that looks like this and it breaks here, and this is what you call E, right? If this is stress and this is strain, stress over strain is Young's modulus. In this case, in the case of the spring, we have force, deformation. Force over deformation, which is the slope here, is the modulus of the spring, but it has different units than the Young's modulus. Okay, modulus is the same thing as saying stiffness. Now, why do I write all this out? Why do we want to look at this before we look at consolidation problems? Well, because they're pretty much the same. That is, this problem and the consolidation problem. If we knew what weight we're going to add to the spring, any weight, the only thing we have to do is come in here and determine the settlement. Not settlement, but the deformation of the spring. Okay? Let's say we're going to put a higher weight. Okay? This is the deformation that will be incurred. Okay? Doing this graphically is the same as using this equation or this equation. They're the same equation. Okay? Now, this curve of force versus deformation, which is a line, is the curve for a spring. Okay? It's very simple. The equation is very simple. For a soil, plot curve is this curve. Here we have stress, which is equivalent to the weight over here. Okay. Force over area. And here we have void ratio. Okay? The void ratio is equivalent to the deformation here. So these are flipped. It doesn't matter. What matters is what the axes are and how they are equivalent. This is the weight or force. This is the stress, force over area. This is the deformation of the spring. And this is the void ratio of the soil. And the void ratio decreases with stress, as we have already learned, right? During consolidation, etc. So we can think of void ratio as equivalent to deformation, because the deformation increases with stress and the void ratio decreases with stress. They are related. Okay, and we saw that in a previous slide. Okay, so the idea is that using this curve, we're going to essentially go about as follows. We're going to say, look, if the stress that we impose in the field is this stress, then that is the void ratio that the soil will suffer the soil will eventually end up at, okay? And the difference between the initial void ratio and that void ratio is proportional to the deformation that the soil will incur in the field. So essentially we're doing what in our problems we're going to be doing what we did for the spring here, okay? But we're going to do it with this curve. It's quite straightforward, actually. Now, where it becomes a little bit tricky, really, not really so much, but where it does become maybe a little bit tricky is in the equation. Why? Because look, this is a log scale, right? This is a log scale. There is two parts to this curve, right? This is not deformation per se, but this void ratio, so we have to convert it to deformation. So at the end we end up with an equation that is not as simple as that equation. I should say this one is the same one, but it's an equation that will provide deformation or settlement as a function of all the other parameters. So for this curve, we're going to have a larger equation with a log in it, etc., because this is a log scale, and you'll see what it looks like when we do the example. But it's very important, I believe, that you consider, that you realize that we are going to be doing for the soil essentially the same thing as we do for the spring. This is the equation for the spring, to determine the deformation of the spring, and I'm going to write out the other equation, that is the equation for soil, which comes from this curve, when we do the problem, okay, as an example.